What is the primary oil recovery? What is the secondary oil recovery? What is the enhanced oil recovery? Let's discuss. In terms of recovery, the oil production can be divided into three steps. The first step is primary oil recovery, in which the driving force for oil production is supplied by the reservoir pressure itself. What we do here, just we drill several wells and start producing oil from the reservoir. Then we're going to have secondary oil recovery. In this step, after producing oil for a while, we're going to notice that the reservoir pressure drops, and as a result, the production will decline. In order to boost the production, we may inject either gas or water into the reservoir to keep the pressure of the reservoir. And then we're going to have the last step of the recovery or enhanced oil recovery. Doesn't matter how much we keep the reservoir pressure high. Okay, assume that we inject a lot of gas into the reservoir, and in a hypothetical situation, the reservoir pressure stays constant, but still we're going to have some residual oil within the reservoir. And the goal behind the enhanced oil recovery, or EOR, is to produce the residual oil from the reservoir. What you see here is the schematic of the secondary oil recovery. As I mentioned before, at the top of the reservoir, we may have some gas cap through which we may inject some gas, or we may inject water to the aquifer below the reservoir. So here, what you see here, the green zone is oil, the red zone is gas, and the blue is water. It is more advisable to use gas because gas has very high compressibility, so it's somehow mitigates the pressure drop better. But it is possible that in some areas we don't have access to gas. For example, if there is a gas reservoir nearby the oil reservoir, definitely we can transport gas from the gas reservoir to the oil reservoir for gas injection. But if we have no nearby gas reservoir, so what we can do, we just can inject water into the reservoir. However, water is less compressible compared to gas, and as a result, it may not be as useful as gas for pressure mitigation. So in order to better understand what we do in enhanced oil recovery, first just let me introduce viscous fingering. That is very interesting physical phenomena that happens in the boundary of two immiscible fluids. Assume that we have two different fluids, and these fluids are immiscible, which means that they cannot mix with each other or dissolve into each other. Example is water and oil. And now consider two different scenarios. The first scenario is that assume that the viscosity of A, here mu is viscosity, is greater than B. Like A is oil and B is water. And now what you see here, the fluid A pushes the fluid B or displaces it. In such a scenario, as you see here, the fluid A 100% displaces fluid B, and you see that the boundary between these two fluids is stable. You see like almost a linear front, and you see no specific phenomenon here. What we call this one a stable displacement. Now consider another scenario in which viscosity of A is smaller than B. So here A is water and B is oil, and A displaces B. If we repeat the same experiment, as you see here, in the boundary you see the development of some finger-like structures that is called viscous fingering. So when A is less viscous than B, or A is more mobile than B, we're going to see in the boundary the development of viscous fingering. And this phenomenon is called viscous fingering. One interesting question that you may ask at this point is that how viscous fingering is related to the residual oil within a reservoir. To answer this question, I'm presenting you the results of an experimental study that was conducted at the University of Calgary. In this figure, you see the setup that was used. Here you see a micro model that is like physical simulation of a porous medium. And we have a camera to record and monitor fluid displacement. This device is a pump that injects fluid into this micro model. And at this point, you see there is a hole to extract fluid out of this micro model. So this experimental study was to monitor the fluid displacement in porous medium when we have two immiscible fluids. The two immiscible fluids used in this experiment were water and oil. The micromodel was initially saturated by oil, and then water was injected into the micromodel to extract oil. So what you see here is the micromodel, and the yellow color corresponds, the white color corresponds to grain's location, and the red color here is oil. So what you see here in the beginning of the experiment, all the pores are saturated by oil. And what we do here, some water is injected through this hole that is transferred to the micromodel through these tubes. And then oil is extracted out of this micromodel from this hole. Now just let's see what happens once we start injecting oil into this micromodel. What you see here, blue means water, red oil, and as I said, white is corresponds to grains. Once the water is injected into this micromodel, you see the development of fingers. So the more water that is injected, the fingers grow more and more. And you see that after a while, a fraction of oil is bypassed by water. So it means you have some residual oil within this micromodel, and doesn't matter how much water you inject into this micromodel. Assume that you just keep injecting water for 10 years, several years. This fraction of bypass oil will remain within this micromodel for good. And indeed, this is similar to something that happens in an oil reservoir. So if just we look at an oil reservoir, here we have gas, and here we have oil, and here we have water at the bottom of the reservoir. So once we start producing oil from the reservoir, we extracting oil from here, indeed water moves upward and flows toward the oil saturated zone. So indeed, it is similar to a situation, the less viscous fluid, that is water, displaces the oil. And as a result, some fingers will develop within the reservoir, and a fraction of the oil within the reservoir is bypassed by water. And here is the fact that we are not able to produce 100% of oil from the reservoir. Doesn't matter, even though we assume that the reservoir pressure is constant during production by injecting a lot of gas into the reservoir. So here the idea behind enhanced oil recovery is to take out the residual oil from the reservoir. Now, Just let me give you a little bit more insight. When we talk about porous media or reservoir rock, we have pores, we have matrix, and we have interplay between fluid and matrix. And as a result, the situation is much more complex compared to the fact that we have like just two fluid with no pore. The experiment that I showed you before, like about two fluid A and B, was from a situation that no pore was involved. But here in real porous medium, we have pores, we have capillary, we have interfacial tension between the fluid within the pores. And that makes the situation more complex. So in order to answer you, when we have stable displacements or fingering in a porous medium, I have to explain the concept of relative permeability first. We are familiar with the concept of permeability. It is a property to describe how a fluid can flow within a porous medium. And we can easily calculate the absolute permeability that is indeed the property of the medium, not the property of the fluid, using this equation. So as you see here, if we calculate the pressure gradient within, for example, the porous medium or a rock sample that we have, and we measure the flow rate and we have some idea about viscosity, then we can easily calculate the absolute permeability. And indeed, the calculation of absolute permeability is very straightforward, it's not that difficult. But it is better to introduce another concept that is relative permeability. Because when we talk about oil and gas reservoirs, we don't deal with a single fluid. So if we deal with a single fluid, maybe the absolute permeability is a good quantity in order to describe a flow displacement within that porous medium. But here we may have like gas and water, or we may have oil and water. We have different combination of fluids within the reservoir. And for that reason, it is better to define relative permeability. Relative permeability is defined at a constant saturation. So, for example, assume that for like some constant saturation, the water saturation is SW, water and the oil saturation is S oil. Say that it is 30%, S oil is 70%. And what we do here within these constant saturations, we measure the flow of each fluid and calculate the permeability for that fluid and divide it over the absolute permeability to obtain the relative permeability. Okay, so what we do here, so assume that once, so here 0. SW is 30%, S oil is 70%. We inject fluid in the core sample, so these two saturations remain constant during the experiment. We measure water flow rate, oil flow rate, from which we can calculate oil permeability or water permeability, and then by divided by absolute permeability, we can calculate relative permeability for water. Similarly, we can do the same thing for oil. To obtain the relative permeability for oil. So something that is interesting here, you may notice that the relative permeability is smaller than 1. However, something that I should tell you here, and it is very important, relative permeability is indeed a function of fluid saturation. So in other words, if we repeat the experiment at another saturation, say SW is equal to 40, S oil is 60, Then we're going to obtain different values for relative permeability. Another thing that I should emphasize here, that the relative permeability of oil plus water is not necessarily equal to 1. Please consider this fact. This plot shows how the relative permeability of water and oil varies with respect to water saturation for a rock sample. So I mentioned that it is impossible to make the water saturation 0. Similarly, it is impossible to make the oil saturation 0. So we're going to have some lowest value for the water saturation, that is called irreducible water saturation, and the lowest saturation for the oil, we may call it residual oil saturation. So as you see here, when the oil permeability is at its minimum level, so here you see that this is SW maximum, and at the lowest possible oil saturation, you see that the relative permeability of water is the maximum. And then once we changing the saturation, we increase oil saturation, reducing the water saturation. As you see here, the relative permeability of oil increases. At the same time, the relative permeability of water decreases. So whenever we deal with a reservoir rock, companies may take the rock sample, and as you see here, this is a device that is used to calculate the relative permeability. And this device is very complex. Indeed, obtaining the relative permeability is more difficult than the absolute permeability, and the device that is used for relative permeability estimation is more expensive. And so usually companies, when they want to assess the reservoir, they take some core samples from the reservoir rock, and then what they do, they put it in this sample holder and obtain some curves like what you see here in order to have a better idea about the fluid displacement within the reservoir. Now just let's go back and answer this question. When we have fingering within a reservoir rock, here is you see an interesting definition that is called mobility ratio, and it is defined by the relative permeability of water over water viscosity over the relative permeability of oil over oil viscosity. So whenever the mobility ratio is greater than 1, we're going to have fingering in the reservoir. On the other hand, if ratio is smaller than 1, we're going to have a stable displacement. Okay, so how we can, here another question, how can we produce the residual oil from the reservoir? Now, if we look at the concept of mobility ratio, then we can answer this question. So we should make the mobility ratio smaller than 1. How can we do that? Either by increasing the water viscosity or decreasing the oil viscosity. For enhanced oil recovery, or EOR, several techniques are used, including thermal techniques, chemical techniques, and miscible processes. Thermal techniques are used to recover heavy oil. In Canada, there are many heavy oil reservoirs that are found in near-surface formations. Heavy oil is highly viscous. Its properties are more similar to wax or tar compared to regular oil that we see in the nature. So in order to produce heavy oil, we have to reduce its viscosity. How can we do that? In general, for heavy oil production, two horizontal wells are drilled. And as you see here, the top well serves as injection well through which high temperature steam is injected. And once we start injecting steam into the reservoir temperature increases. And as a result, oil viscosity decreases. So once the oil becomes more mobile, because it has high density as well, it starts flowing to the production well by the help of gravity. So indeed, gravity causes the heavy oil to move downward toward the production well, from which the oil is extracted out of the reservoir. So this is the process that is used in Canada, and this process is very expensive, and it may become doable in the case that the oil price is high. So in the cases that the oil price is low, because this process, the entire process is very expensive, maybe it is not profitable when the oil price is low. Chemical techniques means that we inject some chemicals into reservoir to increase the production. And when we talk about chemical, we may inject some polymer. So polymer is a kind of highly viscous fluid that is injected into the aquifer in order to push the oil forward. So as I said, we should either increase the water viscosity or decrease the oil viscosity. So here, polymer flooding is indeed similar to a process that we are increasing the viscosity of water. Another chemical that we may use for EOR is surfactant flooding. So surfactant is indeed soap, and in our daily life we use soap. For example, if our hands are oily, we cannot just remove the oil by pouring water over our hands. So what we do here, we apply some soap, and just by applying soap, we see that oil can be removed easily. How surfactant does here, or soap does here, is that it removes the interfacial tension between water and oil. So as a result, water can remove oil easier. Similar thing can be done within a reservoir. Usually, when we talk about chemical techniques, it is possible that we use polymer flooding and also surfactant flooding at the same time. So what you see here in the beginning, a slug of surfactant is injected into the reservoir. It's indicated by the red color here. And after that, a slug of polymer is injected. So polymer is very expensive. We cannot inject a huge volume of polymer into the reservoir, because even like polymer may be more expensive than the oil itself. So as you see here, we inject some surfactant first, and then after that some slug of polymer, and then after that we keep injecting water. So that water somehow pushes the polymer forward, and at the front we have surfactant that somehow helps water to move water easier. So as you see here, usually a combination of polymer flooding and surfactant floodings is done at the same time to improve the production. Another method that we may use in order to reduce the viscosity of the oil is by injecting some gas into the reservoir that gas is dissolvable or miscible into the oil. For example, what we can do here, we can inject CO2. So CO2 can be dissolved into the oil, and we know that when more gas is dissolved into the oil becomes more mobile. So by injecting a lot of CO2 into the oil, we can reduce the viscosity of the oil and improve the production. And indeed, this is something that is done for miscible process. It is possible that we may use other gases as well, But something that has been noticed to be more effective is injecting CO2 into the reservoir. I hope that you have enjoyed this lecture and you have a better idea about different steps of recovery, in particular what we do in EOR or enhanced oil recovery. And I think it's a very interesting topic, EOR, because different methods are used, and it's a kind of multidisciplinary approach to solve the problem of oil production. Thank you very much for your attention.